Hello, welcome back. You guys can hear me? Yes? Let me put the chat box in here. Great, great. How's your spring break? So welcome to week 11, okay? Oh, we had a break? Sorry, you got a fake break. Sorry. The midterm? I guess some of you haven't even started the spring break yet, right? Yeah, it goes very fast. So here's a mini plan for today. We are continue to go through the rest of the contents for PID control. Let's warm up a little bit. So I think I haven't given you the, let me do this. So I haven't given you the quiz. Let me give you the quiz right now. So this is week quiz 11A. So I gave you this one from file, upload documents. So we are in the week quiz A. So you should be able to get this one right now. Yes. So let me open this quiz for you so that we can go through. So what we are going to check with you about AWBT, okay, AWBT, anti-wind up and bumpless transfer. Then we talk about PID tuning table using a relay feedback method. So then you should put a table there. ZN stands for Ziegler and Nichols, okay? Then after that, I hope you draw a block diagram of with an anti-wind up PID control scheme with a practical derivative. Practical derivative. Okay, we are going to review all of them, okay, today before we move on. All right. So first of all, we have seen the PID control. We put a gain in the outside. Inside, we have this is called integration time constant. This is called differentiation time constant. Remember that you have a dt in here, you have time. So you have also a time in here. So this is also in the unit of arrow. This is the same. You have time in here, cancel the time, so you have a unit of arrow. So that's why they write. So everything here is same unit. Okay. Then you multiply by this. Okay. So this is the format. We have many other formats. That doesn't matter. Okay. So another thing is regarding the integration about differentiation. So the S is a differentiation, and this part is a low pass filter. So you can see if you have a noise with a small AN is very small, but after you do a derivative, then the noise got amplified because you have omega here. Your omega will show up if omega is high, okay? Then this is like 100 times, okay? So that's the problem. So we need to do filtering. So this is like going through a low pass filter, okay? So it's a pure ideal or pure differentiator cascaded with a low pass filter, okay? Okay, so this together is called a practical differentiator, okay? Practical differentiator. So in our real world, okay, in our real world, we also have a set point weighting. Okay. So we also have a 2 degree of freedom F, this term, okay. This B is a set point weighting. So you'll see the set point weighting will be able to speed up your the response to a sudden change. So it's called set point weighting. So you have a bigger weight, so you have a faster response. I think that weighting makes sense. So then say, for example, you have a B is bigger, then you can say, oh, I pretend your reference is 2, not 1. So you just chase it faster, right? So that's the idea. And so another feature is regarding the saturator. Okay, you have actuator saturation here. So you'll have this type of wind-up effect. So your output will oscillate like this. So you can check this too. After you have applied anti-wind-up, so you are going to get a response like this. So with no oscillation. Okay. So how we can do that is what they call anti-wind-up mechanism. So before and after the saturator, you check the difference, make the difference being subtracted from this value, then you integrate it. So then you can get out of the saturation immediately. So this is a time constant that if this is very, very big, then this is 0, okay? So you can see with different weighting, okay? The bigger, then you have more, okay? The smaller, the heavier, okay? So you can see it's very small, 0.1. So this is better. You have 3, then you have an overshoot in here. So you can see here clearly the difference. The rule of thumb is if you do PI control, it's half of the TI, okay? And if you PID, you do a geometric average, okay? Geometric mean of these two numbers. So we just do some simple review. So in this quiz, I want you to draw this schematics here. So basically, I hope you are going to draw something like this. So basically, you'll have a saturator here, okay? So then after that, you apply to your real plant, okay? So I hope you are going to do this one. This is a mechanism for anti-wind-up. So this guy is always bigger or equal to this guy. So this is 0 or negative, okay? So then you have a summation of KP here. You have KP in here. So you have a arrow signal in here, okay? Arrow signal in here. So you have KP, you have a KD, you have a KD, you have also KP, but you have something called TD, then you have S, but you also do 1 plus TDS divided by N. N is a number of 4 to 10, okay? So this is called a practical differentiator, okay? So everything here is positive. So then also you have integrator here, okay? And you have a signal in here. You are supposed to integrate this one. They add this one to here. But however, you have something different in here. So you have a 1 over T I. This is an integration time constant. They also have KP, right? Because you have the same KP, we'll use that format, okay? So then this one is coming over here, you have T, okay? Okay, so also plus. But this is actually, this value is usually negative, okay? Okay, it's not positive, negative or zero. When it's no saturation, then this difference is zero, okay? So this is actually a block diagram anti-wind-up PID control scheme with practical derivative is here. So this is my practical derivative, okay? Of course, this is my output. You can also make the whole control system here. So this is your reference. This is your, so this will solve this, the problem here, right? Okay. So you simply say anti-wind-up, you know how to do it. What is a bumpless transfer? Bumpless transfer is in the real world, you have a manual mode versus automatic mode. So you have manual, automatic mode and a manual mode. Okay, you can switch in between 3 modes. In fact, either off or manual or automatic. Okay, automatic. How to ensure when you switch, there's no huge jump. Okay, that mechanism also is a mechanism. Is an idea of how to turn from A to automatic mode to manual mode without jump, okay, without jump. So the basic idea is to have a manual mode, you have manual mode variable here, okay? So you have output in here, okay? So then you have output feedback in here. This is a measured value as well. Then how this value will be also, this, you can see this is the same copy of this one. So your manual input will also give this value here, okay, with this set point. So it's already used in our manual mode as a set point. So it's not sudden change, okay, not sudden change. So here's a list of different industrial PID controllers. They have different structure formats and different features, okay? So we have gone through that, AWBT. So this is, a parallel PID implementation. So this is a differentiator with a practical differentiator. And you can see I have a KC, so it's the same KC, okay? But you have time constant in here. So this is just the PID, but this does not have a anti-wind-up mechanism. So we need anti-wind-up mechanism here, okay? And remember, these are both plus, okay? Because this is always, this value here is always negative or zero, okay? On the other hand, this is only AW. Where is the BT? The BT part is like this, okay? So manual mode, you'll make that one directly add into here, okay? So then how to make it smoothness is same thing applied to here. You have such integration saturation. So this is the same anti-wind-up, okay? Same anti-wind-up is the same as the bottom one. Same as here, okay, in the manual mode. So this is the manual mode time constant in here, okay? Okay, so that's AWBT, okay, AWBT. So with that, today, in fact, we are going to go through, so we talked about PID tuning, okay, about using Ziegler-Nichols rule. One is to do the step response, okay? You should keep asking about what kind of information Ziegler-Nichols tuning used. They need to use the K, okay? K is like a static input and output divided by input delta, okay? You also have L divided by T, L divided by T. So what is this point, okay? I think you should start clearly remember it. So this is called It's called maximum slope point. Okay, what does that mean? So you can imagine that you have something going like this. Okay, so this is your reaction curve. It's called a reaction curve. So let's do derivative of it. What do you could see? So you have a derivative. Okay, it's going up. It's initially it's like this, then going down, right? So going down, going up, and going down. So at here the slope is 0, right? So at this point, slope is going down. Okay. So it's something like this. So this is the slope. Okay. So initially slope going up, then going down. Okay, going down to 0. Okay, this is 0. So this is slope. So what is that the peak slope? So this point is this point. Okay, is this point. It's called peak slope. It's a maximum slope point, MSP, maximum slope point. Okay. Then you identify that, you do a tangent. So what is this point? Okay, it's this tangent. So then you check what is your L, what is your T. Okay. All right. So then L divided by T will give you theta. Use Kp and theta and L also. Okay. You can decide from the table. If you want to do P controller, just use proportional, then your gain should be like this. Okay. All right. Also, you need to check about the format. So when I use TI, TD, and K, the PID format is like K bracket. You have 1 plus TI is 1 over TI, and you have 1 over S. TD is TD and S. So it's something like this. So that format is, remember, it's like this. Okay. Okay. So in a midterm, where I also ask you to try the Cohen-Coon method. Today we are going to go through that. Okay. So, but this is one of the two methods for Ziegler-Nichols. So one is based on reaction curve approach. You retrieve all the numbers and check the table, get this coefficients you need. Okay. So this is called Ziegler-Nichols step response or reaction curve based method. Okay. So another method is talking about critical oscillation method. Okay. So basically, you push the system to the limit under the proportional control only. Okay. So you keep increase the gain then until the system is not stable. Okay. So then with that, you will be able to so this is an example showing you that. So you push the system to the stability limit, meaning make it oscillate, okay? Make it oscillate, like sustaining oscillate, okay? You increase the Kp so that it will become a sustaining oscillation. This is already make the system at the boundary of stability, okay? It's called critically stable, okay? In this case, I check what is your gain. That gain is called KCU. So what that Kp you increase to this point, this Kp is called KCU. I think the U is called ultimate. Okay, ultimate. C probably is a critical control. So another idea is something we want to talk today is called relay tuning, relay feedback. Because if you push the system to the very oscillation state, then it is dangerous. The system might be damaged. So I don't want that. I hope I can control that oscillation amplitude. Still, I can get something out of it. So it's called relay. This is a relay behavior, okay? So it's positive, then it's 1. It's negative, then it's -1. Okay, it's called relay. It's the relay nonlinearity. So it's very easy to implement. Okay, so after you add the relay, so then you can see that relay control signal is either 1 or -1. Okay, -1, or you put the amplitude. Okay, amplitude. So this amplitude is h. Okay, so peak to peak is 2h. Then your output is oscillatory. The output is oscillatory. So then from there, you can measure peak to peak distance here. That is your period, okay? So it's called ultimate period. So then also you measure this peak to peak magnitude is 2A. So with that, we can convert H and A, okay? We thought H divided by A is a gain, right? So no, it's not. Sorry, it's not. Okay, you need a correction of 4 divided by pi. But this is a magic number, okay? This magic number deserves a closer look. It's derived analytically in the textbooks. But now, well, I'm going to share with you later. But now let's accept that you need this. This is a slightly greater than 1, okay? Like 1 point something. So this is a 3.14, okay? So 4 divided by this is like 1.3-ish, 1.2. So just slightly adjust this one and put this one as a KCU, okay? KCU. Then you put the KCU here. PU is your period, okay? Okay. Because TI, TD are just the time dimension. The unit is time unit, right? Okay. So, and remember here, this guy divided by this guy is 4, okay? This is also a magic number, okay? It's a magic number. So you need to challenge it. What if it is not, okay? This is not, so you need, this is a magic number. You need to understand it. This is another magic number. Only recently it was decoded why it should be like that, okay? Originally, the main purpose of having this one is to make a complete square. So that's just for mathematical reasons, okay? And later people say that, yeah, I should put this one like lambda, another tunable parameter, what's going to happen? So people did lots of study on that. So it's called a modified Rackman-Nichols. So you can see this relay feedback is less dangerous. It's widely used in industry, okay? Widely used in industry. So here is our starting point for today. So in industry, if you buy a commercial PID controller off the shelf. Off the shelf is called COTS. So commercially off the shelf, okay, COTS. So you can buy COTS single, this is a single loop PID controller. Inside the single loop PID controller, there is a function called a button. It's called auto tune, okay, auto tune. So basically, if you want to auto tune, you put this T stands for tuning mode. A stands for automatic mode. So then you also have a manual mode, okay, remember. So when you add this mode, your output will start to oscillate, okay, and become a sustaining oscillation. Sustaining oscillation, okay, and then your this signal is either maximum or minimum, okay, or that's 1 and -1, okay. But in some of the processes, you may feel this 1 is too small. Maybe you not need an edge, okay? So this is -H. So you can tune that. That doesn't matter, okay? So then what you do is you check also peak to peak here. This is called 2A, right? So then you go back and use this formula and use this table and decide what controller format you want to use. Then you can get all the required PID parameters, okay? This is also called PID parameter setting or auto tuning. Okay, auto tuning. So this kind of automatic tuning is a standard feature now in the commercial single loop PID controller you can buy from the market. Okay. So the idea is basically you do a relay feedback experiment. Okay. Then you extract those peak-to-peak value and also the period of oscillation. Okay. Then you will be able to set the PID. Then you turn back to this, so then it's can automatically return back the PID. So this is useful when you don't have a good idea of what is the PID. They can do this one for you. Okay. On the other hand, when you are running with the existing PID and you see the system is not doing very well because a lot of things are changing, like some of the parameters are changing. You didn't know, but you observed your Y is not behaving like you wish. What do? Turn this one back to the relay again, and they have oscillation. Then you recompute the PID, then turn back to the PID. The PID will make the output behavior better. So there is a need to look at this Y behavior. So then decide when to retune. This is practically in industry very important. So this is called performance assessment. So you should have something always watching the Y, make assessment, okay? Then the assessment will make a decision and to say whether we should retune or not, okay? That's very practical in the industry, in process industry. Make sense? Okay. So when you in the industry working in a commercial single loop PID controller, you will meet this. So control is not just design a controller here. You also have assessment part, auto tuning part, and then those decision making part, when to retune. Okay. So this relay tuning is widely used in industry. Okay. So its operation manner is close to the real situation. So it's kind of like, you heard about something called, there's a book series. It's called So and So for Dummies, okay? Okay, like Control for Dummies, Drones for Dummies. You just Google it. It's a very big series of like firing text for dummies. And this is a book series, okay? So basically you need to like something called foolproof. I think maybe I used the correct word, foolproof. So it doesn't matter if you are not smart enough. Yes, it's like a self-calibration. It's called a self-tuning, okay? You decide when you should improve your control parameters, okay? I said one button tuning. You have that button said, I want to retune, just press, it will do automatically for you. That's called auto tuning. It's also called auto tuning. There are some dedicated books on this topic, even this 3-4 slides. They do a very like 300 pages long book. And it's also easy to explain to users, work well for all the standard loops with little prior information, okay? So just to make the system being able to have a sustaining oscillation. And it's usually very robust. So this is 180 degrees of because the signal is kind of reversed, okay? There are many other opportunities you can explore, okay? Say for example, so here we thought this is a standard sinusoid, but it may not. It could be something like this. It could be not ideal sinusoid. So what kind of that harmonics can give us more information or not? And I want to put the emphasis here, be careful, okay? We said a little does not mean no, okay? No prior information. No, it's not equals no prior information. We still need to use some of the information, okay? At least you know the system behavior, like sampling, how fast is the sample. That's our immediate next topic, okay? So these are the practical issues we should consider. Say, for example, what if that profile is not symmetric? And so on and so forth. What if the system is not linear? It's a non-linear, okay? But it is an attractive method to do. So let's go back to see the 3-tank process. So you have a tank 1, it's a first order system. You have tank 2, is also first order system with different time constants. So you have tank here, okay, 3. So you have 3 tanks. So you want to make the 3 tanks and you have saturation here, okay. So this is a proportional controller. So you have step reference, then you do a feedback, okay. So let's do a relay feedback, okay. So we put a relay in there, okay. So then we kind of see the system becomes, the signal becomes like this, and my output becomes like, looks like a sinusoid, but it's never real sinusoid, okay? So in this case, I need a 4/pi, 0.5 is my, what is this one? So 0.5 to 0.4, the KCU, okay? So this distance is 1.5, this is 2.5, okay? 1. So is 1, so the magnitude is 2. Sorry, this peak to peak is 1.5 to 2.5. This is 1. So the amp, so it's actually it's 1. But this one from here is like 12.15 to here is like 12.9. Yeah, ish. Okay, so this is like 0.8. Okay, this is like 0.8. So divided by 2 is 0.4, okay? So divided by 2 is 0.05. So this is 1.59. This is the number. So by using that, we can tune our system with a TITD and a case like this, okay? It's PID. And remember, this is 4 times. This is 4 times. It's 4 times of tau d. Okay, did you see that? There's a reason to do that. Okay. That reason actually is also easy to find. So you have k, you have 1 plus t. So say for example, you have a td. So you have tau I 1 of s plus td s. So if I do, so I'll write, so it's tau I s, okay, tau I s plus 1 plus tau I tau d. S square, right? So this is k over tau I s, okay? Basically, I pull out this term out. So I have tau I s, I have 1, I have this one. So in the end, I'm going to have, so I have tau I is 4 tau d, right? 4 tau d in here. So then I have 4 tau d square, s square plus 1 plus this one. So you have 4, this one, this is 4, this one. So what do I have? So this is, I give this 2 tau d s, okay? Do I? So this is 1 plus 4 tau d s plus 4 tau d square s square. So exactly this is this. So I can make a complete square here by setting tau I and tau d. So I give an explanation why we need a 4 tau d is because of the complete square. Okay, complete square. So let's talk about if you are assigned a project to tune the PID controller, you need to decide how you choose P or PI or PID. Okay, so you need to do that decision based on what? So you need to talk about diagnosis and the improvements, reliability, and the field tuning issues. So we are going to talk about it. So when to use a P controller, okay? So if you say, oh, some offset is okay. So if you have type 0 system, then you will have steady state error, right? If the steady state error is allowed, okay, then you just use P control. So like a flow, like level, valve, and so on and so forth. Okay. So, but what if it is not allowed? Okay. When you use PID control, okay. So you don't allow any offset. It's called offset free. Okay. So in that case, you need an integrator. Okay. You need an integrator. Okay. For example, the pressure control in distillation, those pressure must be tightly controlled. Okay. So you assume you have a faster sensor and your loop speed. The overall speed is determined by your process and actuator dynamics, how fast your actuators can perform. Okay. So then when to use PID? Okay. So if you have a system that is sluggish, I want to make it faster. Okay. And you have delays. Okay. Okay. So then PID control is preferred. So we are going to attack this delay issues. Okay. Next, I'm going to immediately tell you how to deal with the delay. But this is next. And also regarding whether your noise level is too high, because sometimes the derivative itself will, remember you have a omega, a sine omega t. You do derivative, you got omega out, right? Cosine. you have sine omega t do this omega is big, then the high frequency noise will get amplified a lot. Okay. So this is temperature control. Usually you need a PID. Okay. You have a large time constant, slow, and you have delay. Okay. So in that case, you should use PID control. But for PI versus PID control, it is also dependent on your dead time and time constant. So tau is usually used as a time constant, and dead time is alpha. But I usually use L, right? Remember, our system is K over Ts plus 1 E minus Ls. So basically, this is talking about L divided by T, okay? So if L equals 1, this is called, they are equivalent. The delay is equivalent to this time constant. But if L divided by T less than 1, that means L is small. So this is called lag dominant. But if L divided by T greater than 1, then we call this delay dominant. Okay. Delay dominant. So we are talking about this. So this is a delay dominant. Okay. So then if the delay is relatively larger than your time constant, then you should use PID instead of PI. But if your is less than half, 0.5, that means it's not, delay is relatively small. Okay, relatively small. Then you use PI is okay. Okay. So if you have excessive oscillation or sluggish, if you use PI control, you get that result. You are not happy. That means you do not have enough tuning knobs. So in here you have 2 knobs. Okay. Here you got 3 knobs, right? So of course you got 3 knobs, you can do better, right? At least you should say potentially you can do better, right? So we have the first order plus delays, K, T, L. What is this one? This L divided by, this is 0.4, this less than 0.5, so you should use PI, right? So this is, I told you, it's called quarter damping ratio, okay? So basically you have up in here, so you basically check here. This is 1, right? Oh no, 0.5 is this steady. So this divided by this, okay? This ratio, this ratio, quarter ratio, a quarter damping ratio. So we assume this is like this guy divided by this guy is 20, is 4, okay? So 1/4. So after second peak, you damped 25%. So this is a QDR. That's the meaning. Okay. So in this case, we designed a system. You can see the performance is good. Okay, it's good. So basically, oh no, sorry, I should mark this one on this Y. This is Y. This is U, not on the U. Okay, so we should say here. So this is Y. So we should do this. This one divided by this one is 4, or greater than 4. Okay. Anyway, so so if you control a gain, you use a smaller gain, then the system is sluggish. Okay, so meaning slow. So from here to here, so you need like more than 10 seconds. But this one, if you increase this one, yes, you have QDR, which is good. So QDR means this and this is 25% or less. So this one is like a doubled, okay? Okay. But if you keep going, you'll have something called a ringing, okay? Oscillatory. So that gain you tune, This is overall gain. Again, I hope you remember this is a KC bracket 1 plus 1 over TIS plus TDS, something like this. Okay. So you tune the KC, you basically tune everybody. Okay. So if you have an integration TI, so it's 1 over TI. So you have a 1 over S. So you increase TI, meaning decrease this weight, okay? The weight of the integration effect is getting smaller and smaller. So if you don't have that, so tau I is decreased, that means your integration is too much, okay? So this is integration appropriate, yeah? But your set point is supposed to be 1, okay? Supposed to be 1. So your integration effect is, you still have a steady state here, but as time goes, you may reach to 1 after a long time, okay? Okay, but this one, you will reach to 1 immediately after a while, okay? So the tau I, this is too small, okay? Too small. Integration is too small. This is too large. This is adequate, okay? So basically you can use the QDR to check, okay, to check. All right, so if you have too much proportional gain, so if you have a system is ringing, okay, it's ringing, so you should check your input and output lag, okay? So this difference, okay, the peak to peak difference, okay? So that means you have too much gain, too much P, okay? Too much, the gain is too big. So you should, then you observe here lag is too small, okay? If the lag is too large, that means your integration is too much. Why? Remember, your integrator is 1 over j omega. So that will give you minus 90 degrees lag in phase, okay? So that's understandable, okay? So if you have a large integrator, increase the integration effect, this one will bigger and bigger, okay? So then you tune I, you will reduce this. So then the ringing will be smaller. So if you in the industry setting, you find out the system is ringing, it's chasing each other, it's bad. Your supervisor is scared. So just record the curve and show him, hey, look, we can reduce the integration gain, okay, and perhaps we should reduce the overall gain, okay. So these are some ideas you can use in industry. So that's talking about oscillation. But what about reliability? So we have non-linearities hidden, okay? It's hidden. So, so maybe the delay is also changing, non-constant, okay? The gain is also drifting, okay? So you have also magnitude of disturbances also changing, and so on and so forth. So in reality, your operational point is here. So you thought your system gain is here, but your gain actually is changing, okay? It's changing. So what is idea to have better reliability to account for these imperfect factors is to make the decay ratio not 1 over 4, but 1 over 10, okay? So means you have this one here, so you better, this one will decay quickly. No, not delay, not decay quicker, okay? More quickly. So that means that's the rule of thumb, okay? to increase the system's reliability. So in a field, how you are going to tune. So let's walk you through this interesting thing. So what do? You do decay ratio, define tuning specification. Say I tune that, so my decay ratio is 1/6. So QDR is 1/4. Okay. So try to be more robust. Okay. So filter design and implementation, turn off derivative and integral parts. So this is true. You always start with proportional control to see what's going on. Okay. So then you know that initial gain estimate is the KC, your critical gain. Okay. And increasing the gain. Okay. So that you can change, you can get the decay ratio 1/6, right? So after you have done that, you decrease this one by 10%. So this is just a rule of thumb. So in that case, you can use tau I as 5 times of your process time constant. Okay, it's my capital T in here. Okay, so then you do a set point change and you decrease this tau I until you see the decay ratio is met. Okay, so that's for a fast process, how you tune. That give you some directions you can try. Okay, so these are summarized from the field. Okay, how to do the PI control. If you have a Zeitlin-Nichols in the frequency domain method, I'm not sure this is appropriate. So basically, you want to talk about Nyquist curve. So usually Nyquist curve like this, okay? So you have a point A, okay? So then you said you have a controller, basically is move A to B, okay? If you know A, if you know B. B is like where I want to be. A is where I start from. So how to move A to B, it is through a controller, okay? Controller. So then you, from the specification, usually it's difficult for you to specify what is your B, what is your A in a Nyquist plot, okay? Nyquist plot. But this is in the textbook, people discuss this. So then you can compute what is your KC, okay? What is your controller? Okay, and also you can compute what's your TD and TI. This is in Astrom's book, 1995. Very famous, published by ISA Press. Okay. So they can say Zeitlin-Nichols also can be interpreted in the frequency domain approach. I think this part, we are not going to put this one in the final exam. This is a more advanced method, okay? Because in reality, the site engineers cannot tell you what is my current A or what is my current B, okay? Or what is my B I want to go. This is not scary. There's a very nice graphical method to do this. They believe this is easy. I feel this is not so obvious to most of the site engineers. But you do know that there are other ways to interpret the Zeitlin-Nichols tuning method. Okay. So basically, we are not talking about the frequency method here. We're not talking about it. So we prefer to do a step response, okay? Step response. So, but in the step response, we hope have a good SNR, signal to noise ratio. So if you signal to noise ratio is infinity, then that means your noise is 0, okay? It's noise free, okay? But if your noise is like 10% of your signal, then signal divided by noise, it will be like 1 divided by this one. I do 20 log 10. This one will give you what? 20 dB. So when you say 20 dB as SNR, it's like saying that your noise is only 10% of your signal. Okay. So 20 dB SNR is considered as 10%. Okay. All right. So so other classical method, we talk about stability limit method. We talk about KCU, PU, and we did a relay, right? So we prefer this. We don't use a traditional stability limit method, okay? That is potentially will damage my system, right? So we are going to do a Cohen-Coon method, okay? So slightly sophisticated than the Zaglos-Nichols method, but they will not give you a quantum leap. There are other methods. Do you know how many tuning methods? There are about, safely say, over 1,000 different tuning methods. So I'm going to show you. I made a collection here. So I have a directory called RAT. It's not an animal. It's called Relay Automatic Tuning. Okay, Relay Automatic Tuning. So I'm going to show you a book. So can you see this? This is a book called Handbook of PI and PID Controller Tuning Rules. So this is a book with a collection of all existing tuning rules. And how many pages? 623 pages. And it's in the 3rd edition, so it's constantly adding new rules into it, okay? As I told you in industry, 90% of the controllers are in PI or PID type. So if you have a rule included in this book, people will remember you. But unfortunately, there are just too many of them. So I have something here. So this is a table to scare you. So because depending on your system models, so some of the tuning knobs, they need first order, this is a plus delay. First order lag this is just like a FO first order PTD model, is like we said. So like this one. Yeah, oh, you have seen that's first order plus delay, okay? This is a second order plus delay, okay? And without a zero, meaning nothing in the numerator, okay? So basically, we learned everything here, depending on the model format. So they had 6 classes of models. We only focus on the model 1. So for the model 1, there are how many tuning rules? 649, okay? For different sections or equations. And for other types of the models, so they have this amount. So together in this book, there are 1731 tuning rules included, okay? So just to give you a rough idea, okay? So, but among them, Cohen-Coon is one of those widely used methods. So I'm going to show you this. Can you see this table? So basically, you have a reaction curve. You do a K0, which is this, okay? Then you get the tau 0 is T1 divided by T0, okay? So this is a tangent, okay, with maximum slope. That is the peak slope point, okay? Peak slope point, MST, okay? So as usual, okay? Then I think also we have this section T2, T2 minus T1 is V0. So then you just put in this equation, okay? This equation, all right? So don't ask me why, how they come out this magic equations. I think I know the trick is you have different types of system, you do lots of simulation, and then you summarize a tuning rule like this. I personally also summarized the tuning rules I published on this before. They're kind of interesting. Don't have time to explain to you. So you follow the step, you will be able to get a KP, TRTD. Again, this KP is overall gain in the bracket. Inside, you have an E and TR or TD, okay. So why they don't use TI? Interesting, my pen is no longer working. That's not right, something wrong. Anyway, it's okay. So I want to tell you why they didn't use TII stands for integration. But do you know that previously integration is also called reset, R-E-S-E-T, reset. So this R here is stands for reset, okay? So reset. So this is called Cohen-Coon reaction. It's a one of the famous tuning method. So if you know Zagos, Nichols, if you know Cohen-Coon, people will say, I know you know. PID tuning, I know you know. Okay, so that's why it's important to know this. Okay. Now I'm going to give you satisfy your curiosity. Let me see, now it's working. Now it's working. It's strange. So let me show you one more thing here. It's called, let's look at this one. So basically it's also easy for you to try. So it's actually invented by Astrom and Hagland in 1984. Okay, I met both of them in 2018 PID workshop conference. Yeah, I met both of them. And Hagland is Astrom's PhD students. So automatically can get your sustained oscillation for the critical frequency P sub U, okay? P sub U, okay? Now it's done in a closed loop, okay? So this the whole system can be kept within bound. You are not going to jump like crazy. You make the system damaged, okay? Okay, and this can be analog, okay? So it can be done just for do an analog relay, the system start to oscillate. So it can be analog. It's not like if you don't have a computer, fine, you just make the system oscillate. Yeah. So here is the fun part. It's called DF method, okay? DF analysis, describing function. So basically you assume your E is like this, right? E is like this. Yeah, sinusoid relay input is a sinusoid, but your output is a square, okay? This square can be written as this one, okay, as this one. This is a Fourier series expansion, okay. And so ratio of this is important, fundamental component of U. So I cancel all others. I just leave the fundamental one. I only need when K is 1. I ignore anything higher than 1. Then when this is 1, I have sine omega t. Because 2 times 1 minus 1 is 1, okay? But remember, I have 4 divided by u in front, okay? That's why you have this thing, 4 over pi, and you have mu divided by a, okay? So this is ratio of the amplitude, okay? So you have sinusoid, so this is a, sinusoid is a, and this magnitude is mu, okay? Magnitude is mu. So that's why you have a magic 4 divided by pi is due to the Fourier series expansion. As these are residues, okay? Residues. We assume that these residues can be ignored. Okay. Okay. So I think I gave you the mysterious why we have 4 divided by pi here. Okay. Because this only expands the sinusoid as a what they call a fundamental component. Okay. So in other words, okay, so you have a system like this. This is a Nyquist plot. So when you have oscillation, that means they have a meet in here. So this is your meet. The omega is linked to your oscillation. Okay, oscillation. So so if you have an amplitude that's different, okay, so then this different, if you change this this side, this distance can be tuned, okay, can be tuned, okay. So you can tune this amplitude here, okay. And some people will introduce this is called hysteresis. You come over this way, you go back this way, so called hysteresis. So switching points is plus one. So this is called relay with hysteresis. Okay, relay with hysteresis. So then this is related to hysteresis size. Okay, so therefore you can tune what is the frequency you decide. And of course, filtering hypothesis is I have a system where we can filter out all those high frequency parts. So I think we talked about all these PID related issues. Yeah, for lag dominated dynamics. Okay. So Zagreb-Nichols usually is not ideal, but it gives you a starting point you can improve. And many people propose the improvements over the Zagreb-Nichols. And this one has has some tuning rules. This is the tuning rule. And this is called modified, okay? Modified tuning rule, depending on talking about KLT, TS plus 1 E minus LS, KLT, depending on that, okay? So then you can, depending on L and T, okay, L divided by T is called relative. So less than 0.1 is very small delay. You use this equation. And between 0.1 to 2, you use this equation. If it is greater than 2, you use this equation. So depending on how dominant is your delay, okay? That makes sense, okay? You kind of be like, use the same rule for all different delays. So that's called modified. So you can see when we modify that, we have balanced L and T is equal. So you can see the dotted line is Zagnall-Nichols, okay, Zn. This solid line is modified like before, okay? Okay. Let me hide this one. So when L, the delay is very small, then when delay is very big, okay? So again, so you can see they reach to this one and have a return back. So otherwise it's too slow. So when L is very large delay, the Zagnall-Nichols original one is too slow. It will be too slow. It can reach to 1, but it's very slow. But modified one is reasonably fast. Okay. So this is Cohen-Coon. You can do some comparison if you can try. Yeah, it should work. It's a very famous Cohen-Coon reaction curve method. So the procedures, I think you know that. So we are done with we are done with today's lecture. So what we try to do on week 11b, we are going to do first part, second part. So in the end part, I'm going to have 30 minutes of our final project orientation. So please be there, okay? But we are going to record it anyway. So we are doing a 20 minutes talk plus 10 minutes QA, okay? It's very important, okay? If you want to get a solid A, you have to do very good job in the final project, okay? So then I got 45 minutes also type of thing talking about a few important concepts. So like Euler parameterization, like Smith predictor approach explained, and then even a PID controller using this idea, this Euler parameterization idea. Okay, so I think this topic is quite important. I think in the beginning I should add another one. It's called IMP internal model principle. Okay, so with that, please do not miss next lecture. There are some very important concepts I care a lot. I feel like if you don't know this, you should not claim you learn anything from me, okay? All my students must know what is the internal model principle, what is the Euler parameterization, what is Smith predictor, okay? Those can be done in 40 minutes, okay? So get ready. Until midnight, submit your quiz. It's not very hard, just help you to warm up. Yeah, 40 minutes, it will be enough, okay? Those are very interesting concepts. You are ready to receive those messages, okay? Okay, so anything from chat box? Yeah, if you want more, I can spare some time later, okay? But we need to really switch to the digital control part. Oh, by the way, we have 2 homeworks left only, okay? One is on digital control, okay? Another one is on sensors plus actuators. So then you should focus more on your final projects, okay? And lab works. So we only have 2 homeworks left, okay? All right, talk to you later. And everybody take care. Go get vaccinated. Okay, bye-bye then. How I can get out, I don't know. Oh, it's here, stop sharing. Oh, cool, thank you. Bye-bye.